cross-partial property of conservative fields. Let F equal PQR be a vector field on an open simply connected region D. Then PY equals QX, PZ equals RX, and QZ equals RY throughout D if and only if F is conservative. So these equalities hold true if F is conservative. So that's 3 dimensions because my F is PQR, and that's a 3-dimensional vector field. It says the version of this theorem in R2 is also true. If F equals P comma Q is a vector field in an open simply connected domain in R2, then F is conservative if and only if PY equals QX. Now look at this exercise below. It says, for the following exercises, determine whether the vector field is conservative. If so, find the potential function. So this is a 3-dimensional vector field here, so it's this top case I'm dealing with here. So I'm going to have to find PY, QX, PZ, RX, QZ, and RY. So it's a lot of partial derivatives to find there. So I'm going to rewrite this first for my sake. And understand that this is P, this is Q, and this here is R. And what we're going to do now is we're just going to start finding all of those partials. So first we need PY. Okay, so PY is going to be this with this YE to the Z with respect to Y. So PY is going to equal EZ. E to the Z. All right, and then we need QX. Now, QX should equal PY if it's conservative. So QX is going to be the derivative of X e to the Z with respect to X. So that's going to be E to the Z. So they are equal. So by just this first condition, it's looking like they're conservative. So let's try the second one now. So now we need PZ. Now we're here. So PZ, so this is with respect to Z, so Y e to the Z. So the derivative of e to the Z is e to the Z, so that's going to be Y e to the Z. It doesn't change. Okay, so now we need RX. And R is the last one here with respect to X. That's going to be Y to the EZ. Okay, so those two are also the same. So now we got the last equality here that has to hold true here. So we need QZ. And QZ would be the middle one here. So X e to the Z with respect to Z. And that would be X e to the Z. These are nice, easy partials. And then RY. So now for RY here, that's this one with respect to Y here. So X, Y, e to the Z with respect to Y. So that's going to be X, e to the Z. So those are also the same. So what we see here is all three of those partials that we had to compare were equal. So that tells us then by the cross-partial property of conservative fields, F is conservative. There we go. All right. So there it is. We know it's conservative now. So now that tells us we can find the potential function. So now keep in mind here, if it's a potential function, that means there's some function f that if I take the gradient of it, that it's going to equal this p, q, and r. And that's going to equal my f. So that means if I take the partial of f, now this should be an fx, this here should be an fy, and this here should be an fz. So what's going to happen here is my p should equal fx, my q should equal fy, and my r should equal fz. So that's what we're looking for here. So now we're going to have to take this first component here and integrate it with respect to x. So, and these integrals are going to be pretty nice to work with too. So x e to the z dx, and that should equal my f partially. Okay, at least. Okay, so this is going to be x y e to the z plus c. Now I'm going to integrate the middle one here. Now that's supposed to be with respect to y there. So that integral of x e to the z is supposed to be with respect to y. So then that's going to be xy e to the z. So then the third one here, which is the r here, that's supposed to be my fz here. So my fz is supposed to be my r. So I got to integrate the third one with respect to z. So xy e to the z dz. And the integral of e to the z is e to the z because the derivative of e to the z is e to the z, and x and y are just going along for the ride. So x times y, e to the z plus c. Now if you notice this, they are all exactly the same. So my function then is going to, my potential function, let me be more specific about this, is going to be x, y, e to the z plus c. So there's my second part of what they were asking me for here. So once I do these partials and I find out it's conservative, I can actually find that potential function just by simply integrating each piece with respect to x, y, and z, the p, q, and r, respectively. Okay, so there's our answer.